Lagrange error bound. So we know that error, represented by r for remainder sub n, is equal to the absolute value, the actual value of some function represented by an infinite series, subtracted from the approximation, or subtracted by the approximation of that function by some partial sum of a series. Now, an error bound is a worst case scenario maximum possible error shown by r sub n being less than or equal to some maximum error. Now, how do we find this maximum error? Well, we know that a series can be represented as p sub n is equal to the formula for a Taylor series, the nth derivative of f of c times x minus c to the n over n factorial. Now, a series with one more term than this, which would be a more accurate approximation of the function this is modeling, can be shown with p sub n plus 1 is equal to p sub n plus that other term, that last next term, f n plus 1 c times x minus c to the n plus 1 over n plus 1 factorial. Now, because this term here is the only difference between p of n plus 1 and p of n, we know that the maximum possible value of this term has to be greater than or equal to the remainder we find when using p of n, because if this term was less than the remainder, then p of n plus 1 would be a worse approximation than p of n, which we know it isn't. So we can say that r sub n is less than or equal to the n plus 1th derivative of c times x minus c to the n plus 1 over n plus 1 factorial. And that is the maximum possible value of that. Now, because this term doesn't have a max and this term doesn't have a max, the maximum operator only applies here. So this can be rewritten as Rn is less than or equal to maximum f to n plus 1 c x minus c plus 1 factorial. And the absolute error bars, the absolute value bars, are because this is error and it's always positive. Now this itself can be rewritten as r sub n is less than or equal to the absolute value of the n plus 1th derivative of f of z times the other stuff. Where this z is some value between or equal to c and x, which gives the maximum possible value for this derivative. Now, this formula we've gotten to is known as Taylor's remainder theorem, or Lagrange error bound. Now, how do we actually use it? Well, let's look at a problem. If we have a fourth degree Maclaurin modeling cosine of x approximating cosine of 0.2, what's the Lagrange error bound? Well, let's start plugging things into our formula. So we know that it's a fourth degree, so our n equals 4. It's a Maclaurin, so our c equals 0, and we're approximating 0.2, so our x equals 0.2. Now this z value can be found by finding the maximum value of this n plus 1 derivative, which in this case would be the fifth derivative of cosine. So let's look at the derivatives of cosine. So the first derivative is negative sine x. And the second derivative, negative cosine x. And the third derivative, positive sine x. The fourth derivative, positive cosine x. And our fifth derivative is negative sine x. Now, to find our z, we need to find the maximum possible value of this negative sine x. Now, most of the time, you would just plug in c and x to this function and see which one is larger, right, to find the maximum. But in this case, because we're working with sine, we know that the maximum value of this function has to be 1. So our z is equal to 1. Now we just plug everything in. 2, 1 times our x is 0.2 minus 0 to the fifth over 4 plus 1 factorial. And we solve. Now, this right here is our error bound. This value is the maximum possible error for our approximation of cosine at 0.2. This is our Lagrange error bound. And that's it.